electrons, basically. The fermionic character implies two things. And they're actually believed to be related to each other, but they're different. One of them has to do with the spin of the electron. The spin of the electron is half spin, and that means that the spin, as far as the spin goes, if we forget about the orbital motion of the electron and so forth, the electron has two spin states corresponding to spin a half, plus a half and minus a half. The other property that qualifies the electron as a fermion is that it satisfies the Pauli exclusion principle. You can't put more than two of them into the same state. In talking about the states, spin counts. So if, for example, we ignored the spin, and, for example, we talked about putting two electrons into the ground state wave function of a hydrogen atom, yes, you can do that. You can put two electrons into the lowest energy level, but only because you have the spin to soak up the Pauli exclusion principle. And so you put them in with opposite spin. If you try to put a third one in, you can't put it into the ground state. If you try to put a third one in, let's say because we're dealing with lithium, plus for helium, we can put both electrons into the ground state. In the approximation that we ignore the interaction between the electrons. In other words, in the chemist's bad approximation, incidentally, these days chemists are very sophisticated quantum physicists, really good chemists, and they're very sophisticated. But, you know, the old picture of the atom, the shell model, and all those sorts of things that were simplistic, which didn't work very well, but, you know, they work a little bit. You can put two electrons into the ground state of the helium atom, so the helium atom behaves as if you had two electrons both in the lowest energy state, and that's okay because they have opposite spins. If one is up, then the other is down. If one is down, the other is up. In fact, those two electrons are entangled. They're entangled in exactly the way that, well, they're entangled. One is up, the other is down, one is down, the other is up, and that's an entangled state. Once you go to lithium, you can't put another electron into the ground state, and I don't mean into the ground state of the of the helium atom. I mean, of course, into the ground state of the electron wave functions in the vicinity of the lithium nucleus. The lithium nucleus also has a charge, and it also has a collection of wave functions for electrons. You can put the first one into the ground state, you can put the second one into the ground state, but then the third one has to go into another state. Simply no room for it. By room, I mean from the point of view of the exclusion principle. So you start filling another shell. And how many energy levels are there at the next shell? Well, we can draw our energy level picture that we drew before. Angular momentum 0, which is called the S wave, at least for the simple approximation in which the electrons don't interact. There's the ground state, and then there are excited states which still have angular momentum 0, and so forth and so on. And then there's the P waves. The P waves are angular momentum 1, or orbital angular momentum 1. P stands for something I don't know what. And the first P wave has more energy than the first S wave, and it has three states, the three possible states of orbital angular momentum 1. And then there are above that, and by the accidents, or they're not really accidents, of course, but by the funny mathematics of Coulomb potential, the first, well, there's degeneracies, extra degeneracies that I've indicated here on the diagram, and so forth and so on. SPB, that's spectroscopic notation. At the next level, at the next angular momentum, this is L equals 0, L equals 1, L equals 2. At at the next, at the D wave level, L equals 2, the lowest energy state is already up to here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So forth. 5 states for L equals 2. And that's what the pattern of energy levels looks like. Okay, so you go to the lithium atom. The lithium atom, you put in 2 electrons into the lowest energy state. So they're both in the lowest energy S wave state. And now you have an extra electron you have to do something with. Well, you could put the extra electron upstairs at some higher energy state, but it would be unstable because it would decay by emission of a photon, which we haven't gotten to, but it would decay down to something of lower energy. What you can do is put the next electron into any one of these 4 states. Okay? Keep going. What comes after lithium? I can't remember. Beryllium. Okay, then you come to beryllium. Beryllium, you fill the lowest one, and you fill one of the next levels. But wait a minute. There's 4 electrons now. So you fill 2 of them. That's beryllium. What comes after beryllium? Boron? Boron? Okay. And the one after boron? Ooh, carbon. Good. Right? And if there wasn't spin at the next level, at the next atom, which is what is it? Nitrogen. At the next nitrogen level, you would have to start filling up these up here. But that's not the way it works. The spectroscopy and everything we know about it is consistent with putting the 5th, is it the 5th electron? 1, 2, whatever. The next one fits in again into one of these levels, and that works until you've gotten to neon? Neon. Okay? The neon, there are 8 electrons in this first excited energy level here. Why are there 8? Well, one for each orbital state, but you also have the spin degree of freedom, so there are 8 states that can be occupied here, and then beyond neon, I don't remember my chemistry, whatever. Sodium? Yeah. Right. Sodium is the next metal. And, right. You have to put one of them up here. And you know the story. I mean, you know the story as well as I do. Valence electrons and so forth. Sodium looks sort of like hydrogen, and so does lithium, because it has one extra electron in the outermost electron orbit, and so forth. I didn't want to do chemistry tonight. I just wanted to remind you that 2 things seem to go together: the exclusion principle and the spin a half. Now, could you have, here's an interesting question, could you have particles which will spin a half but didn't have an exclusion principle? You could put a spin a half. Oh, before I talk about that, let's talk about photons. Do photons have an exclusion principle? Photons most certainly do not have an exclusion principle. And in fact, classical electromagnetic waves are typically waves in which many quanta photons are all in the same state. That's what makes them classical, that they have a very large amplitude, a very large number of photons all in the same state. And so photons most certainly don't have an exclusion principle. In fact, it's almost the opposite. There's a tendency for them to want to be in the same state, but of course photons don't want anything, but they do tend to congregate in the same state. Whereas fermions, the half-spin particles, can't be in the same state. So you might ask, could there be a particle of half-spin which doesn't satisfy the Pauli exclusion principle? Or could there be a particle of integer spin? Photon is an integer spin particle, spin 1, or even spin 0. Could there be one of those which does satisfy the Pauli exclusion principle? And the interesting fact is that they go together. Half integer spin, that doesn't necessarily mean spin 1 half. It could be spin 3 halves, spin 5 halves, spin 7 halves. Those half spin objects always satisfy the exclusion principle, and the spin integer particles never satisfy the exclusion principle.
Instead of theoretical,
that's a theoretical result.
Something.
It can be derived from the principles of quantum field theory. We won't get to that. But I'll show you a little demonstration tonight. All you need is a belt to understand some aspects of it. There's some interesting topological aspects of it which we'll try to get to. This is... No, it's not. That's correct. That's correct. It's not a theorem.
And it's also not true in 1 or 2 dimensions.